I'm going to use the cosine.
Well, I thought I would just give a little overview and try to connect all these different subjects that we're supposed to cover. And they may look a little confusing at the times, but I'm trying to tie them together in terms of physical effects rather than actual individual problems. This, if you find it confusing, this is because it's Scott's fault. It's supposed to be Scott's job to connect everything. So, okay, I'm going to talk slightly. Can I just shout?
I think you're supposed to turn off some of the systems. People, we did that just, yeah. It's
If it's all right, I can just shout. Okay, great. Okay, thank you. So I'm going to first just talk briefly about the astrophysical context. I'm going to start from big, and this is the only slide on cosmology I will talk about. Large-scale structure, clearly gravitational dynamics is important. It tells us about the parameters of the universe and the clustering properties and emergence of structure.
Well, can you just put it on the slideshow? So
Oh, yeah, right. Yes, okay. I thought I did that. Forgot. Okay. There you are. Okay. Of course, a lot of people in this room have interests on galactic structure, all the way from spiral structure remains and still technically challenged problem, and to elliptical galaxies, and with the next generation observational instrumentation. Maybe I'll just put it out on the table. Okay, you unlock it now. Okay. With the forthcoming instrumentation like Gaia, we will have incredible data to analyze the history and the structure of the galaxy, the Milky Way, and try to understand the assemblage of these island universes. And another context, as we go down in scale, is at the very center of these stellar systems, where you have massive black holes. One of the questions is the formation and evolution of massive black holes, and what drives AGNs, and especially in the context of galaxy formation. How do we understand things like ISIMA relation? How do we understand this neutral interaction, and the origin and the dynamics of all these S stars near the very center of our own galaxy, and as well as high velocity stars. They not only tell us about the structure within the galaxy, but also help us to probe the distribution of dark matter in our neighborhood. Many experts in this room have been responsible for our understanding of stellar clusters, all the way ranging from globular clusters and to open clusters, and globular cluster and dwarf galaxy here. And today, with observation from Hubble Space Telescope, we can actually get down with the color magnitude diagram all the way to the hydrogen burning limit. And from there, we can study questions concerning their dynamical evolution, their chemical evolution, and among other things. In the context of dwarf galaxies, and perhaps they were the seeds of larger entities such as the Milky Way, especially in the context of lambda CDM. And in that case, one of the key questions is what had led this diverging evolutionary path between dwarf spheroidals and globular clusters. Dwarf spheroidals have lots of dark matter around them. Globular clusters have very little, and dwarf spheroidals have lots of signs of continuing star formation. Globular cluster the star seems to be mostly coeval, and there are some later generation stars. And their distribution around the galaxy also seems to be somewhat different. And go down to smaller scales, we look at things like open cluster, OB association, and more importantly, perhaps we look at star-forming regions, and this helps us not only to understand stellar dynamics of small systems, but the very process of star formation itself. Inside these clouds, we see a large number of starless cores whose core mass function are very similar to that of the initial mass function. There are already signs of mass segregation before even stars start to appear. Now, perhaps to me, certainly has been an exciting ride in the last 20 years, and this is really the discovery of the blue dot. And in the last 20 years, since really the first clearly identified extrasolar planet has been discovered around the main sequence star, and there have been lots and lots of new data and new information, and the blue dots are those which were detected by radial velocity, and the red dots are those which is detected by transit. So this is a perhaps the most rapidly advancing field in astronomy and astrophysics today. Now, already we are starting to get enough information to do statistical analysis to move to make a transition for planet formation, theory of planet formation, evolving from a case study to a branch of science. And because we can have testable hypotheses. They are not only very common, but their dynamical properties are very diverse. And many of these extrasolar planets have eccentricity goes up to the range of almost unity. And so they have a lot of difference in masses, and they have also, they reside in multiple systems. In the last 3 years, perhaps the best boost to this field has been provided by the Kepler Space Telescope, which enable us to detect planets with sizes down to sizes comparable to that of Earth. And as we can see, that they are extremely common, and perhaps one in every 2 stars that we can already detect signs of these planets. Furthermore, many of them are in multiple systems, and some of these, for example, here, the yellow dot represents those are in 4 planet systems, and the red dot have 6 planets, and there are many more new ones that have been discovered. So common existence of planets are in all over the place. Okay. And if you look at these multiple systems, looking at their period ratio, and you can see there are certain structures, they're not randomly distributed, and many systems are near, but not exactly on resonance, and I'll talk a little bit about that later. And most of these systems are nearly coplanar. In fact, they're so coplanar that at least one of these systems, or 2 planets, actually transited each other. Coming closer to home, we have the solar system exploration, which had led to tremendous advancements in our understanding of the chronology that took place in the early part of the solar system. We see that by looking at meteoritic data where we can see tracers of radioactive isotopes, and we can actually date back to the time that when these things are formed, how long it takes them to get into these most primitive chondritic meteorites within 20,000 years. And we also see that many of these gas giants, they seem to have cores in them, and although they tend to be very diverse and somewhat uncertain, especially in the context of Jupiter. In Saturn, there is clear evidence that some sort of core is needed. We also see their kinematic properties, and most of them lie in the plane. In fact, this is exactly what motivated Laplace to propose the nebula hypothesis. And but today we also see there are a few outliers which are on inclined orbits. Their spin axes also provide some dynamical clues on the formation of these systems, and they are not only their origin, but perhaps even their dynamical evolution. And if we go to systems such as smaller planets and minor planets, and here are an asteroid, but what is particularly interesting about these asteroids is not only that they are covered with craters, which suggests a process of assemblage through coagulation, but also many of them have little satellites around them. Many of them are spinning up like crazy, and this type of process tells you some clue about an important dynamical process may have taken place. If we look at asteroids today with SSS and with HST, we can start to do many interesting statistical analysis, and not only we can get this semi-major axis distribution where we see definite structures at resonances of Jupiter, but if we look at inclination distribution, we also see groups, and which suggests perhaps some of them may have been a family that was broken up during a collision, a major collision. And you can also see this in the size distribution, which is not quite like MRN distribution, but perhaps with a break. And signs of resonance are also found in the azimuthal distribution. If we go a little bit further afield, one of the most interesting regions is beyond the orbit of Neptune, where we see in the last 10 years or so, discovery, I don't know, about thousands maybe, of KPOs. And they provide a sense of clue on the origin of short period comets, and their distribution give us interesting information perhaps about the rearrangement or the migration of orbits of major planets. But what is also very interesting is that some of these objects are very large, and they have sizes to be significant fraction of the moon. And these objects are in the outermost part of the solar system, where dynamical timescale is long and supply of building block material is sparse. And how do you get these things formed at the first place and get them into the orbit, especially for this system with CITA, whose periastron distance is actually considerably further away than even the Kuiper belt, the main belt region. Turning attention to the moon, and we today find evidence from isotopic distribution. Perhaps the moon of the Earth was formed after a giant impact, and a considerable amount of study has been made to study this type of process, and that involves capture and And there's a very good example which Norm Murray had looked at, and is the orbit of a moon around Neptune, which is rotating around Neptune in a retrograde orbit. The dynamical evolution of these systems are extremely interesting. They may not only form in situ, but also be captured or through giant impacts of various kinds. Now, if we look at the most famous moon system of them all, namely the Galilean moons, it's well known already to Laplace that they are in these incredible resonance system, and these systems may have excited their eccentricity and then led to tidal dissipation and give rise to the to the volcanoes. Similar system is also found around Saturn, and however, the plot thickens because there's an interwoven set of resonance between Mimas, Titus, Enceladus, and Dione. Now, Mimas is closer to Saturn, but yet its terrain is ancient, full of craters. Enceladus is further away, and in principle should move away slower than Mimas. Both Mimas and Titus are in 2-to-1 resonance, or actually 4-to-2 resonance, and Dione and Enceladus are in 2-to-1 resonance. But Enceladus have these plumes that's coming out, and with very young surface, which suggests some very intense internal heating, which cannot yet be explained by existing theory. In addition to satellites, there are moons, and in fact, this is an area that has been pioneered. Its theoretical study has been pioneered by Scott Tremaine and along with Peter Goldreich. And today we see that the interaction between the moons and the rings can not only lead to this kind of structure, and globally, locally, and even in terms of, you can see the shadow here. And then the most recent, I forgot to bring up that particular slide, even show the formation, possible formation of a moon in the outer region of these rings. They all provide clues on the formation of planets, among other things. Okay, so that's the typical context. I just want to briefly talk about something you already know everything about, so I'm going to go very quickly through this. It's just about some time scales about these physical problems. We're going to start very simply with a two-body problem, and which is the root of Newtonian concept using F equals to ma, that Newton was able to determine one over r squared force law, and therefore was able to work out the elliptical figure of an orbit that satisfied Kepler's laws. Now, these elliptical orbits can be described in a fairly general way by eccentricity, semi-major axis, and some orbital elements such as the direction of longitude of period epsilon and the longitude of ascending nodes. And you may wonder, why do you bother with all these things? Because in principle, around the point mass, these quantities don't change. And on the time scale of a single orbit. Okay, so these are time scale of a few years. Okay, but as you see from the equation of motion, very simply, and the equation of motion is nonlinear because the force is not proportional to r, but 1 over r squared, but it can be solved very easily, and there's an exact analytic solutions for it. And you can, now, if you want to do a little bit more sophisticated, and you can go to throw in another body. In fact, this problem immediately led to sleepless nights for Isaac Newton, and when he tried to understand the precession of the moon's orbit, and he said that gave him the biggest headache, and because then it started to become, extremely complicated very quickly. Now, but this can be simplified to some extent, and many of you have already done this, and with a restricted three-body problem in which you have one body here, and let's say the sun, and the earth, and the moon. And then in that context, if you assume the orbit of the earth is on a circular orbit around the sun, and then you can start to work out and neglect the mass or the feedback of the moon on the earth, and you can solve this set of equations. Now, the problem with this kind of problem is that, you see, the potential of the earth is changing all the time. So the best way to try to figure out something that is that has a conserved quantity is to go into a rotating frame where this thing does not change. Okay. Now, at the later stage, when Hamilton came along and to develop the Hamilton method, and he links symmetry with conservation. Now, by having a frame that is time-independent energy of some sort is conserved, but because it's not rotationally symmetric, and therefore angular momentum is not. Okay, so nonetheless, you're able to work out things like a simple constant, which is known as Jacobi constant. Go over. Yeah, it's a Jacobi constant, and you can work out this kind of. There's a dot. I don't know how to put dots on top of this, and dots over here. But anyway, and this is Jacobi constant, but you can write down this is constant of quote unquote energy integral, and these are constant along orbits. Okay. Now suppose we take out this quantity of motion, and we can work out things like what is called equipotential surfaces, and from these equipotential surfaces, a natural scale comes out, and this scale is commonly referred to as the Hill's radius, and it is proportional to the mass ratio to the 1/3 power. And from there, you can also work out these equipotential surfaces, and you find relative to the planet, within the Hill's radius, things are dominated by the gravity of the planet. And one can start to do interesting thing with it, and looking at, within this orbit and the sphere of influence, things are bound to here, but what is the probability of getting into this region from outside? And one can examine orbits starting from Capillary circular orbit, and what is the distance that is away you can actually get into here. And this distance is something like square root of 12 times the Roche radius. But also you can see that you have these type of orbits, which tells you that in these orbits, if you look at the guiding center, and they go around like a horseshoe, and around the horseshoe there's also epicycle motion, and so there are a lot of fairly intuitive things you can do with that. Well, Laplace was not satisfied with this because he was interested not in the Earth-Moon system, he was interested in the Galilean satellites whose mass are comparable. So he was interested in a less restricted three-body problem, and he still wanted to have the two moons to be much less than the central object, but they are comparable to each other, and so he tried to expand this in terms of these orbital elements, and try to understand systems by expanding the dominant source term to higher order terms. And he referred to these as disturbing function. And you can read all about that in Marine-Dermott. Okay, so the best way to think about that is to orbit arbitrage the motion of a satellite relative to the other satellite. So if you do that, okay, you're not worried about this round and round motion. You're looking at the long-term motion. These are called secular interaction. Okay, so on the time scale of the secular interaction, because of potential, again, it's approximately time independent, because you're already arbitraged out. So energy, quote unquote, is conserved. Okay, but in this arbitrage sense, now once again, the shape is not translational invariant. Not rotationally invariant, and therefore that conservation of angular momentum is actually violated. Okay, so you can solve this type of equation by looking at things like eccentricity and longitude of periapse, and you can see that they go through these type of secular cycle, and the total angular momentum is conserved, but the individual's angular momentum is not. And the energy conservation tells you that to first order, semi-major axis is conserved. Okay, I'll quickly go through this very quickly. This is kind of boring to most people. Okay, so now I want to look a little bit more on slightly longer term and try to use this type of result to look at things like dynamical relaxation and two-body relaxation. Now, dynamical relaxation is process associated on the time scale of one dynamical time scale. Okay, and the typical type of problems are related to realization, related to violent relaxation, phase mixing, and things like that. Okay, and maybe this would never happen, but because today people believe in merger process and lambda CDM, things build up gradually, but nevertheless, this is an interesting problem on its own. Okay, so there is some aspect how complete the phase mixing is, and how does it lead to things like NFW profile, and during this process, even when the violent relaxation is not complete. And then I'll talk a little bit about two-body relaxation. I'm sure that will be discussed a lot by Douglas and in a later stage. I just want to show you this toy problem of a body of n number of particles, okay, equal mass with homogeneous density. So in principle, they should all collapse towards the center because the dynamical freefall time is the same at all radii. And but we know that this will relax, and the key of the problem is how small does it get before they bounce? Would it bounce back into a homogeneous sphere, or would it bounce into something else? You can see halfway during the collapse, already you can see structures. Now, and then this structure eventually get phase mix, and so what's going on? Well, although they're all free falling, you may think they are really undergoing violent relaxation, but everybody is moving with a neighbor whose speed is more or less the same as that. So their gravitational cross-section is actually quite large. As a result, two-body relaxation along the way of two falling towards the center already become effective. You can have, this is the velocity, inflow velocity, and you can have orbit crossing, and eventually you get a spread in the arrival time at the center. When that arrival time and the spread becomes comparable, you get a bounce. And the outcome of that bounce is actually a core halo structure, and in the sense that there are materials that's already gone in and starting to come out, while the outside still continue to come in. So there is, the time symmetry is broken. Now, whether that will lead to NFW or not, ways to be investigated. Okay, now two-body relaxation is probably a little bit easier to handle because one can break down the time scale for phase mixing with the dynamical, the background changing time, the potential change. Okay, so you can actually look at things with almost center of mass conservation and all that, and then you can just look at the phase-phase diffusion rather than a shock. Okay, so now today we're aided by these spectacular observations, Hubble Space Telescope's observations in cluster like 47 Pacini, and you can actually go down, not only see all of the stars there, but also find evidence for mass segregation and relaxation to take place, and compare this with things like numerical simulations and analytic derivations on these relaxation process. And eventually, will this lead to the formation of intermediate mass black hole remains a challenging issue. Okay, so now I'm going to look a little bit on a smaller scale, okay? And the smaller scale I look, it's probably a little bit easier to handle. And we now look at things like planetesimal evolution. And I'm sorry, I'm jumping from subject to subject. I'm trying to link together with the physical process. I hope that is, you're okay with it. Okay, so now I'm going to talk a little bit about scattering and collisions, phase-space distribution, isolation mass of oligarchs, and what does it mean? And eventually I'll talk a little bit more about planetary systems. Okay, so now the difference between the globular cluster two-body relaxation and the relaxation of a disk of planetesimals is that the planetesimal actually moves almost in the same direction with the same speed, but in addition to their velocity dispersion, and they also have a little bit extra relative velocity due to the difference in their semi-major axis. We can look at the standard two-body calculation and ignoring, for the moment, the tidal perturbation from the sun, and you can do that with an impulse, okay? And you can work this out. You can, afterwards, you can put it back in and work out things in terms of action angle variables and all that type of thing. And then you can actually try to look at this cross-section. You can work out the scattering. This is the scattering result, and that gives you a slight deflection. Here you can have also collisions, and if you have collisions, that could also change the momentum during this process. You can do the same type of Fokker-Planck approximation. Today, of course, most people tend to do n-body, but if you want to try to understand this in terms of better detail, you can do this as Fokker-Planck approximation to get things like a scattering contribution and then the dissipative collision damping contribution. Notice there is a coefficient restitution, and if these guys really stick together, then epsilon equals 0. If they bounce, epsilon equals 1. So this is the dissipative process, and here is the scattering process. And you can compare this with what you would derive from two-body relaxation in a stellar cluster. You find, in fact, after you get rid of all the different variables, the main difference is this log lambda. And the reason there isn't a log lambda in the context of planetesimal disk is because you can't go infinitely far away. The velocity becomes larger and larger. The relative velocity becomes larger and larger. So how do we determine collision timescales? And we can get the normal cross-section, but in addition, there's a gravitational focusing, and this is well written in Bini and Tremaine.